trying to identify our surfaces, right? So if we just, like, if I take a snapshot of this and then put labels on the surfaces so that we know how to relate the names with the pictures. So let's see if we can do something like that. So here are 4 surfaces. What would you call the first one? This is the first one right here. What would you call the first one? So the main shape is a paraboloid. And if we make cross-sectional cuts, they look like ellipses. So elliptic paraboloid. The main shape comes in either a paraboloid, a sphere, or an ellipsoid. And if we get hyperboloid of 2 sheets or hyperboloid of 1 sheet. So those are paraboloids, ellipsoids, hyperboloids. Those are the main shapes. And then depending on the cross-sectional cuts, this elliptic paraboloid, the elliptic part is really not that important. It's more like a descriptor as to what would happen if you would make a cross-sectional cut. And the only other type of paraboloid we would probably want to consider would be a circular paraboloid where a cross-sectional cut is a circle. Okay? So the word elliptic in this case is not really all that necessary. So in the choices, I don't know if they had elliptic paraboloid or if they just had paraboloid, but the main shape is a paraboloid. How about this one? Cylinder. So this is the main shape, but can we be a little bit more descriptive? So in this case, it's a circular cylinder. How about this next one? So it's another cylinder, right? But this time it's a little bit different. The cross-sectional cuts are ellipses. And then this one? Parabolic, because I don't see another. Usually for hyperbolas, there's ups and downs, and so this is just a downward parabola. So I would call this a parabolic. So for this, it looks like there's 3 cylinders and 1 paraboloid, and just to distinguish the 3 different cylinders, we would throw an adjective in front. Circular, elliptic, or parabolic.
Why is this one cylinder?
Because it's being swept across an axis. So it starts off with just a parabola, it's being swept. Over here, you have ellipses, but as it goes along this axis, the ellipses change, sizes. Okay? Let's see if we can do another set. It has a variety. I just realized there's one more shape that I didn't talk about. The cone. So what's this first one? It's also, if you want to get a little bit more descriptive, a little cross-sectional cut would produce an ellipse versus a circle. So we might want to say elliptical cone. But really it's a cone. So now that we're talking about cones, or let's do a little side note on cones. The general equation for the cone is z squared. That's not a z. I guess it doesn't matter. Is equal to y squared plus z squared. X squared is equal to y squared plus z squared, for example. Now, how is this different from, say, an ellipse? It's not equal to 1. If we bring everything to one side, it's equal to 0. So it's not an ellipsoid, I mean. Not an ellipsoid, not a hyperboloid. And how is this different from a paraboloid? All of the terms are squared. Okay? So a paraboloid, one of the terms is not squared. So that's the main difference between cones and everything else that we've studied. Okay? So you might see a cone look a little bit different if you took the square root of both sides and then you take just the positive or just the negative side of something, then you're just going to see one part of the cone. But technically, you would get two parts of the cone like this. The next one, it kind of looks like a sphere, but it looks like it might be stretched out a little bit more. So what would you call this? Ellipsoid. So if you look at an egg or a rugby now, you should think ellipsoid. How about this one down here? Yeah, if this thing kept on going down, it would be the hyperboloid shape. But as it is, it kind of gets chopped off at 0, which is still a hyperboloid. This is a hyperboloid. And remember, when we're talking about hyperboloid, there's two types. There's one with one sheet and one with two sheets. And what would you call this one? One sheet. Okay, so if you look at those power generators, nuclear power plants and stuff, you should think of hyperboloids from now on. And then the last one, we've seen this one before. This is another cylinder, elliptic cylinder. Okay. So we good with shapes? Good answer. Yeah, what's the bottom right? Let's do another set real quick. So the first one is pretty easy, right? Parabolic cylinder. Next one is a cone. This one is what? Hyperboloid. Now this one. It's sideways. Don't let that throw you off. It's a saddle. What's it called again? Backwards. So it's one of those. The equation. Let's see. What letter is that? It's a Y. So it's going along the Y, and then the X and Y gives you the paraboloid that points upward, and then the Z is a paraboloid that goes downward. So this is kind of like a paraboloid, except instead of a plus in the middle, it's a minus in the middle. So that makes your cross-sectional cuts hyperboloids. So this would be a paraboloid where you would actually specify that this is actually a hyperbolic paraboloid. So it's essentially a paraboloid, except it's not. It doesn't look like the dish paraboloid that we think of as a paraboloid. Okay, good. All right, let's number 10 on this section. Let's take a look at number 10 and see how that problem looks like. It says to find an equation of a surface obtained by rotating x is equal to 5y about the x-axis. So this is like Calc 2 stuff, right? You take one of these equations and then you do some rotation. So I think if I write this as y equals mx plus b, the b is equal to 0. So it has a y-intercept at 0. A slope of 1/5, which is not steep. And then we're going to rotate it about the x-axis. So what are we going to get? We're going to get a cone, right? So instead of going through that process of drawing the line, rotating about the x-axis like you did in Calc 2, we can actually express this cone with a set of equations. So if we want to keep it around the x-axis, this is the y, and then the z can be going outward. We can redraw this with a slightly different perspective. It's not necessary. But the point is we want this opening along the x-axis, right? Which is what we had over here. It's opening along the x-axis. So if you draw it pointing at you, the x-axis pointing at you, then it'll be opening towards you. So let me talk a little bit about cones some more, and in general how these things would look like. Again, a good graphing program would be really ideal, and if we can start up a little discussion board in web access, if you have any links of interesting graphing programs online, you can feel free to share. Yeah?
Shouldn't the axes on the three-dimensional picture be the y and z swapped with
I think the axes are correct. If you imagine the z coming straight at you on this xy plane, and then you do that view rotation so that the x is here, the y is here, the right-hand rule still applies. Wrap your fingers around the x and then the y, your thumb's going to be pointing up along the z. I think it's okay. Should we graph it and take a look at it from different points of views?
No, it just seems like it seems like the top of the cone is, yes, it's opening up on the x-axis, but the y-axis is actually its vertical direction to me, just looking at it. And then the z is like the weird offshoot should be the y, right?
Well, if I put a little mark over here, like if I punch a little hole here on top of the y, and so on top of the y, that hole that I punched off will be over here somewhere. So this is the y going up, this is the y going up.
Oh, okay. Okay, I see it.
Yeah? Okay. All right, so the general equation for I don't want to call it standard, but I think I don't have any other words for it. A cone would be z is equal to x squared plus y squared, and that would be a cone that's opening up towards the z. A positive and negative z. Okay, so if you look at this equation, it's the two variables on on the other side would give you your something squared plus something squared, and then that would be that would give you the circle that's sitting out here. And then your other variable on the other side is going to be the direction in which the cones are opening toward. So I think over here we can start off this possible equation for this as an x squared is equal to y squared plus z squared. Are we good so far? Okay. So now this isn't quite it though, because this is one of those 45-degree perfectly that kind of a cone. But this cone is actually squashed down a little bit towards the x-axis. So how are we going to compensate for that squash? I think one way to compensate for that squash is that if we look at this equation, x is equal to 5y, this thing has squashed down along the y and the z, right? So it's a thinner looking cone than what we would normally get. So I think if we kind of mimic this equation over here and have a multiplier for the y squared and the z squared, then we would squish that down a little bit. So I guess my only question is that multiplier 5 or is it 5 squared? 5 squared? So I think the idea is that if we take the square root of this, we would get something similar to what this equation should be. Now I know that x squared and y squared are together and you don't take the square root separately, but I think if we put a square there, then you're going to have that form of the equation that you want. So it looks like that would be the equation of that surface, and we should, I guess, take a look at it and see if it's true. Shall we? Let's try to graph it first. X squared equals 5 squared times y squared plus z squared. So it looks like a flattened out cone that we just been talking about. And then if you want to look at some numbers, like what happens at this point where I punch that hole, let's say when x is equal to 4, your y value is going to equal to x equals 4. No, I want to do something else. X equals 10. That's a nicer number, right? Y is equal to 2. So if I just let z equal to 0, assuming I'm flat on the xy plane, when y is equal to 2, hopefully I would get x is equal to 10. So we got x squared is equal to 25, 2 squared, is that 2 squared? 2 squared plus 0. So x squared is equal to 25 times 4 is 100. Take the square root and you get positive and negative 10, but we're looking at the 10. All right, let's check the answer on the actual worksheet here. X squared equals 25 y squared plus z squared. Did I close that? Can't see. Because because if I take the square root of both sides, I want it to kind of look like x squared is equal to 5y squared. I know there's a z squared in there, but if we look at it flat, that's what we want. So since there's x squared and y squared plus z squared, they're all squared, might as well take 5 and square it too and see. Might as well. I can't see if I put that last parentheses here. Oh, looks good. Okay. All right. Any questions? You guys probably have a lot of questions, but you know, you do these problems and then you graph these things on some special graphing program or some program, some online graphing calculator or something like that, and then the more you do it, the more you get used to it. And you should, because later on in the semester, I'm going to say, okay, we need an equation of an ellipse or an ellipsoid. I need an equation of ellipsoid. Can you give me an equation of ellipsoid? And you have to know how that equation would look like. Or if I look at something, you know, what kind of graph is this? Does this look like? Does this look like a paraboloid, hyperbolic paraboloid? And you should be able to tell me these things. And I used to give an oral quiz when I had a smaller class. I would, you know, you guys would be doing some work, and then I'd take one person at a time outside and flash up 5 cards. And if you get it right, you get 2 points. If you get it wrong, you lose 2 points. And then sounds fun. We should do that, huh? I just say no. Okay. That's when we used to have small classes and nobody wanted to take these classes. Or maybe nobody wanted to take my class. I don't know. But it's one of my favorite parts of Calc 3 was the oral quiz on quatric. Okay. Yeah, let's move on. All right, we are talking about vector-valued functions, and we defined vector-valued functions. We showed pictures of vector-valued functions. And I wanted to take a look at a couple of homework problems regarding vector-valued functions. There aren't very many, but
Oh yeah, that was hard.
yeah.
Do that one. They took us long time.
So the one before we kind of did in class, at the end of class last time, the helix intersecting the sphere. And there's a few more things that I do want to do that's kind of similar to this. But I wanted to address some of the homework questions. So let's take a look at this particular homework question. And here they talk about intersecting again. So let's see if we can answer these questions. Oh, what's this? Okay. 2 particles traveling along space curves. Find the point in which the paths intersect. If an answer does not exist, then write DNE. So it's like those what do you call it? At night, those star. What do you call those things? No, when you see them flying through the sky.
Fireflies?
Shooting stars. Thank you. It's like those shooting stars, right? I think I talked about the shooting stars and what they are, right? What's happening is that there's a comet that flies through our solar system, and then we're rotating, we're moving around the space in the solar system, and at some point, when the comet flies through, it leaves the trail of dust and things, some particles, maybe is golf ball size or maybe basketball size. So it leaves a trail of these dust, and when our planet goes through that path, we see it burn off in our atmosphere, right? So the idea there is that those planets, the planet and the comet meet at some point, but they don't meet at the same time. Because you know what would happen if we met at the same time, right? And we got this asteroid or this comet going towards our planet, and we need to blow it up and all kinds of stuff. And then we're going to watch the movie Armageddon, or there's two of them that came out at the same time.
Deep impact.
What? Oh, Deep Impact, yeah. So, in any case, there's a difference between the paths crossing and the paths and the two particles going at the same time. Okay? So what we need to do is we need to think about these things as paths crossing, which means if we let these vector-valued functions be run by the independent variable t, that's your parameter, if they were to intersect at this point, then they're going to cross that point at different times t, different time t's, different t values. Okay? So maybe the Earth over here would cross this at sometime in November, and then the comet would be crossing this sometime in June. Okay, so totally different times. And so to compensate for the different times, we should use different t values, different t parameters. Because all we're concerned about is trying to figure out what the x, y, z, what that point in space is. So that's what we'll do. The points where the particles collide, so this is the same time t. So let's figure this out first. Let's let the first particle, R1, be run by t. And let's the second particle, R2, let the second particle, R2, be run by a different parameter, and let's call it S for now. And this is similar to what we tried to do about two lines intersecting, right? They actually gave you two different parameters for the two lines intersecting. But that's the same idea. Those two lines may not intersect at the same time, but they could intersect at some point somewhere. So 1 plus 6s, 1 plus 30s, and then 1 plus 26, or 126s. So that's your second parameter, a different parameter. Now, if we solve for this, we're going to solve for three equations, and we're going to solve for s and t. If for some reason we get s and t to be exactly the same, then that means the Earth and that comet are going to be hit at the exact same time. Okay? But if there are different times, then this is when November and June or whatever, the different times that they would meet at this point. And so we know at this point we're going to see the shooting stars. All right, so we'll set them equal to each other. The idea of intersecting is setting a bunch of things equal to each other. We got t is equal to 1 plus 6s. We got t squared is equal to 1 plus 30s. And we got t cubed is equal to 1 plus 126s. Now, they are not linear anymore. The t is going to be squared and cubed, so they're not a nice linear system of equations where we can do matrices or whatever other fancy stuff that we might have learned. So the best we could do is take one and plug it into the other kind of business. So t is already solved for the first one. Let's take that t and put it into this t, and then we'll solve for s. So we got 1 plus 6s quantity squared, that's the t that we're going to substitute, is equal to 1 plus 30s. And now we just have an equation with just an s in it. Let's solve for s. This is going to be easy. It's going to be a quadratic. We got 1 plus 12s plus 36s squared is equal to 1 plus 30s. And since it's a quadratic, since its s is being squared, we want to bring everything to one side, see if we can factor But it looks like we got a bonus here. We got the ones cancel, and then we just have 36 s squared, and then bring the 30 over, is that 18? And so s is either equal to 0, or we can even take out an 18, right? 2s minus 1. So s is either equal to 0 or 1/2. Okay. So let's take the s when it's equal to 0. S equal to 0. Our t then would equal to 1 plus 6 times 0. So this is one pair of possibilities. And let's take s equal to 1/2. And then we've got t is equal to 4. Okay, so they're not these at this point they're not at different they are at different times, so we know that we're not actually going to collide. Okay. All right. Now to find the values, we should put this into the third one to make sure that it actually would intersect, because maybe we might totally miss each other. I mean, space is a big space. And so these wires, the path, the vector valued functions are just paths. So imagine them as wires. So if you have two wires up in space somewhere, there's not a very good chance that they're going to be hitting each other unless we set it up that way. So let's see if they actually hit each other. Let's take s is equal to 0 and t is equal to 1. And let's put it into our third equation to see if we're going to get a true tautology, it's called, a true statement. So we got 1 cubed is equal to 1 plus 0. So this works out. So we know for sure we're gonna hit at least once, or the path is gonna cross at least once. And then let's take our other one. S is equal to 1/2. T is equal to 4. So 4 cubed, 64, is equal to 1 plus half of 126, 63. Oh, look, it fits. So it looks like this thing actually would cross paths at two different places. So we would be seeing shooting stars twice a year. So what is our answer? Our answer, they want smaller x, but they want the actual point in space, x, y, z point. So we know that s is equal to 0 or t is equal to 1. So you can take either one of those. If I put t is equal to 1 and put it into my t equation, t is equal to 1, this would be the notation I would use. And so this would just be 1, 1, 1. So I know I'll be hitting this at some point in space. The point in space is going to be 1, 1, 1. Or similarly, you could have put 0 in for s, and you should get the same point, right? Because after all, we found that these components are supposed to be equal to each other when s is equal to 0 and t is equal to 1. All right, we'll do the same thing for t is equal to 4, or when s is equal to 1/2, whatever seems to be easier for you. I'll put R1 and 4, the t value. So I got 4, 16, and 64. So if we put those values, if we put s equals 1/2 into the R2 function, then I'm going to get the same point. Okay? All right, so that's it. The smaller x value is 1, 1, 1. The larger x value is 4, 16, 64. Pretty cool, huh? All right. Any questions? All right, let's continue talking about more about vector valued functions, and let's see if we can try to I don't know. Try to do something fun. There's no fun things in this class. Do you guys remember? Is that funny, the remembering part? You guys remember that the Earth goes around the sun in an ellipse? Okay. Do you remember? Do you remember the polar coordinate function that did this? Not that I expect you to remember off the top of your heads, but in your notes, maybe. Do you remember the eccentricity was like 0.9497 or something? So the other way from 9.4. So it's close to 0, which makes sense because it's almost circular. And so do you remember what the equation was? I think we just made up the equation, right? It was like, so there's that D that we need to worry about, the directrix. This is the focus. And so the other focus would be, I don't know, have you guys heard about some of the 2-star solar systems with 2 stars that revolve around each other? And then, anyways, we're not talking about that. But if we were, it would be another focus point. What?
That's probably over the telescope.
Oh, yeah.
They have the bipolar,
Yeah, binary star system, yeah. That's kind of cool. Did we come up with the equation?
Yeah. D is 5.66.
So your polar coordinate equation R is equal to what? .66 times 10 to the 9th. Whoa, what happened? Okay. Oh, I have to multiply this by... I think we need a new connection here. Okay. So this is your equation for what was it again? The path of the Earth going around the sun in polar form. So let's do this. Let's write this in parametric form. Do you remember how to write a polar function in parametric form? Right? So R equals f of theta, and that changes into into parametric. So it'll be R, which is f of theta cosine theta, and then R, which is f, again, sine theta. Right? So this is my function, f. Ooh. Now I don't know if I want to do this. All right, we're doing it. Now what we're going to have here is, what are we going to have? We're going to have a parametric equation. R is equal to this big thing. And I'm just going to call this D and E for now. Okay, so I'll put DE over 1 plus E cosine, and then instead of theta, I'm going to call it T times cosine T. And then Y is going to be DE over 1 plus E cosine T, and then times the sine T. You see that? Is that cool? Did that work out okay? Yeah, it's cool. So now let's put this in 3 dimensions, and let's assume that this thing is just going to be rotating around the sun on a flat plane. We can assume that, right? And let's just say the plane is the xy plane. So if I was going to bring this up to 3 dimensions, what is this going to be? 0. Because if I say it's on the xy plane, then z is equal to 0 on the xy plane. Good? All right. Let me take this graphing calculator program and see if I can write this equation neatly. I don't know if there's anything neat about this, but let me write this one time. F of x is equal to 5.66 times e, or 10 to the 9th power, and then multiply that by the eccentricity, 167. Divided by 1 plus the eccentricity times cosine of x. So I'm just going to call this f, and then I'm going to define my function in 3 dimensions. As being equal to the f function that I just defined. So f, and this time I'm going to use the variable t because I want this to be a parameterized curve, cosine t, f of t, sine t, and I'll say z is equal to 0. I can't see it. Probably messed it up, huh? Oh, yeah. It's it should still be okay. What's 10 to the 9th? We got to zoom out way. Nine zeros, right? Oh, there he goes. Whoa. All right. So we have the orbit. Now, according to my t value, this goes around from 0 to 2 pi. Earth doesn't go around the sun from 0 to 2 pi, does it? How long does it take for the Earth to go around the sun?
1 year.
Okay? All right, let's do, we'll do one for years, or let's do days? 365.25-ish. Now, how do you suppose we can work on this so that at day 0, you're at a certain point, and then at day 365.25, you're back to where you started from? So I want to change my period from 2 pi to 365.25. How am I going to do that? You need to put a multiplier in t. So we want to change the period to this, so that the multiplier next to the t would, from 0 to 2 pi, we'd actually get there from 0 to 365.25. Do you remember what that b was that you would change your period to? So what should the multiplier be? So essentially what I'm trying to say is that we want to insert a b next to the t so that we have a period of 365.25. So what do we need to do? What? 365 over 2 pi. Remember that? No. Okay. Right. So remember back in trig? That the period for a trig function is equal to 2 pi over b, or is it b over 2 pi? Are you sure? Are you sure? This is your standard curve, sine curve. If we increase this, what's happening to the period? It's getting smaller. So, for example, if I put this now, the b to be equal to 2, what's my period? Pi. Think about that. B is equal to 2, your period becomes pi. So it's 2 pi over b. All right, that was close. Good thing you guys aren't taking trig final, huh? So to find the period is 2 pi over b. And so if you want your period to equal to 365.25 and you would solve for b, what should your period be, or what should b be? I think it's 2 pi over 365. Okay? Yeah.
So then t would go from 0 to 365.
Yes, t would be your time in days now. It would go from 0 to 365. 0 to, yeah. Okay? So we good? let's put that in our cool graph. So instead of a t here, I'm going to want to put a multiplier b. And for this, I'll just say b equals, what was it again? 2 pi over 365.25. And then we want to take our t values from 0 to, what's about half of 365? 180. So this is about 6 months. Wait, that didn't work. Oh, no, I didn't. I didn't put b here. So this is starting from the positive x-axis. Our Earth would have gone just halfway through the revolution, halfway around. Okay? Let's draw the Earth. Well, let's draw the sun. That's easier. Let's say the sun was an ellipse or sphere. I want this. Do you guys know what the radius of the sun is? Look it up. Anyways, so for some people who are looking up the radius of the sun, for the rest of you, what is the equation of a sphere centered at the origin? X squared plus y squared plus z squared equals to r squared. So, do you guys find the radius of the sun?
Yeah, it's 695,800 kilometers.
Was our original count here in kilometers? All right. Yeah, so what is it in miles? 432,450. And let's go ahead and square that. Can't see it. Let's add another 0. Make it bigger. There it goes.
Make the sun bigger.
Because we couldn't see it. So I'll just exaggerate it a little bit. So there's the sun. And so we should draw the Earth. Yeah. We'll make the Earth almost as big as the sun. Yeah? Yeah. So in this parametric equation, it's assuming that one of the foci is the origin. And so when we put the sun at the origin, it's actually the foci, and this thing's revolving around the origin. All right. So we got the path of the Earth, and I was interested in trying to draw the Earth. And this is more programming, I guess, in terms of trying to get this set up and trying to see the Earth go around. This vector, this is really a vector, right? It's a vector just written in columns. It's a vector function. But this vector function is the position of the Earth with respect to the origin at some point t. Okay? So if I was interested in mimicking that or finding that Earth, I want a sphere representing the Earth that's centered around where it's supposed to be. So here's the challenge for you, is to think about the equation of a sphere whose center is going to be this vector at a given point. Yeah?
Is it the equation of the sphere, but for the x and y and z, you put x minus that equation, y minus that equation?
So this vector is really a point, right? And this is where you need to be. So what I would do there is I would say x minus the position where it's supposed to be. And the position where it's supposed to be is this point, or is this is the x component position. And then the y, same thing. And then the z is just 0. And then, so the radius of the Earth, let's say the Earth was as big as the sun. Now, this is at any point t, so I want to change my parameter, and then I'm just going to call this n. And this is where the programming part comes in. All right? Not satisfied in the given ranges. No. It's the Earth that I was trying to draw. And I'm trying to make it go around, maybe instead of n. No, I don't see it. So the idea is to have the Earth go around. All right, well, let's not worry about the picture so much, and let's go back to the equation that we have so far. And I'll see if I can attempt to draw it. So far we have this equation, x, y, z is equal to this big mess over here, right? And so far what we have drawn is the Earth, is the sun is at the origin, the Earth is going around the origin. Now, the moon revolves around the Earth, right? And for simplicity, let's assume that the moon goes around the Earth in a circular orbit, just so we don't have to worry about another ellipse. Assuming that the Earth is the center of this orbit, can you give me the path of the moon? How far away is the moon from the Earth? This far? So give me, should we just make it up, or you guys want to look it up? There's some of you guys that have been on the computer for the whole time, so you just Google up distance from the Earth to the Moon. Miles? Let's do miles. So let's say it's 238,900 miles away, right? And this is orbiting around the Earth, and we're assuming that the Earth is our center. So give me parametric equations for x and y that would describe the circular path around the Earth. Sine and cosine, right? And then if we just attach this r, that would be a radius. I suppose we should use t in parameterize, since we're using parametric equation. The variable really doesn't matter, but I think for conventions it's good to use t. And then again, if we want to see this kind of flat on the xy plane, we would tack in another z is equal to 0 business, right? Okay. All right, so now here's the really cool part that I want to get at. What if we go back and have the sun be the center? The Earth is going to revolve around the sun, and at the same time, the moon is going to revolve around the Earth. So now, if the sun was the origin, how can we follow the path of the moon? So, hold on. Let's let other people try. But here's one way to think about this. Remember that these parametric equations are just components for a vector-valued function. And a vector-valued function is a drawing mechanism that draws a vector from the origin to some point that you're supposed to be in space, 2 or 3 dimensions, right? So we have one vector-valued function that describes the sun as the origin and the Earth as a particle moving around. And then we have another vector-valued function that describes the Earth as the origin and then the moon moving around it. So from the sun, I want to get to the moon. What do I do? Just add the vectors from the sun to the Earth, and then you add the Earth to the moon, and what you have is a vector-valued function that describes the path of the moon. Does that make sense? So, if you can just put that together, so we'll call this the path of moon with respect to the sun being the origin. What would we do? We would take our first function. What's our first function? This big mess over here. Let's call it, I'm going to write vertical vectors so just to make it easier to read. So ED1 plus E cosine, and then we had a B in there, right? BT times cosine BT, E times D, 1 plus E sine BT, oops, cosine, same cosine, and then this is a different sign, and 0. So this is a path from the sun to the Earth, and then if we just add the path from the Earth to the moon, 238, 900, cosine. Oh, we need to talk a little bit more about this. I'm going to leave some space here. (238, 900) sine something t and 0. So, how many days does the moon go around the Earth? Or yeah, how many days? 28. Right, it's 28.
The sun rotates, that's why we have days.
So the moon goes around the Earth in 28 days, right? It makes one full rotation. So what's our multiplier for this? Let's keep the 28. 2 pi over 28. So if we multiply this by 2 pi over 28, then our period for the moon going around the Earth is 2 pi over 28. Okay? So here's your vector valued function to show the path of the moon as the Earth goes around the sun. Now, if I would have done this properly, you would actually see it, see the Earth going around as the moon goes around. But those multipliers, the distances are really too big. So maybe I'll do a scaled down version of this just to see how it might actually look like from a slightly scaled down perspective. It'll be cool. Maybe you should do it. Hey, if you guys do it, I'll give you 5 points for the test. So if you draw the path of the Earth to the moon using some sort of graphing program, and you're free to scale it if you want to. Scale the you can't change the eccentricity, but you can scale the directrix and scale the distance and stuff like that. Then if you show me that on a computer program, take pictures and stuff, and then screenshot by Monday, then I'll give you 5 points for the test. All right. See you guys.